Today I'd like to talk about divisibility, and specifically divisibility by 7. That answers the question, if we have a number n, a whole number, is it possible that we can write n as 7 times k, where k is also a whole number? Now, this assumes that you know the times tables. You can tell if most 2-digit numbers are or are not divisible by 7. This will be helpful for numbers that have more than 2 digits, or maybe 2-digit numbers that are bigger than the ones that you recognize, to bring them down to the size that you do recognize. So this will work for any number of digits greater than 2. But as an example, let's just say we have a 4-digit number, A, B, C, D, where each of these is one of the digits. The first step, we're going to take A, B, C, D and split it up into 2 pieces. The first piece has all the digits besides the last one, and the second piece is just the last digit. So if we had 5 digits, we'd have the first 4 on the left side and the last one on the right side. Next, we combine these together. We take A, B, C plus 5 times the last digit. That's always going to be 5 no matter how many digits you have. This forms a smaller number than the original one. It'll probably only have 3 digits, but that might not be small enough yet. So then finally we just repeat. You're going to keep doing this until you get to the level where you do recognize that the number definitely is or definitely is not divisible by 7. All right, so for our first example, let's take 3,752. In our first step, we split it up into 2 pieces, 375 and 2. In our second step, we multiply the 2 by 5 and add that to the left part of this. This will be equal to 375 plus 10, which is 385, which is still not small enough to tell whether it's divisible by 7 or not. So we're going to repeat the process. The left 2 numbers form 38, and the last one is 5. We're going to multiply the last digit by 5 and add those together. 38 plus 25 equals 63, which we recognize is equal to 7 times 9. So that means that 3,752 was divisible by 7, because when we followed this process, we eventually led to a number that we knew was divisible by 7. For our second example, let's take 68,895. We're going to take all the digits besides the left one and rewrite them 6, 8, 8, 9, and have the last one on its own. Now I combine these together by multiplying the last digit by 5 and adding it to the first 4. This turns into 6,889 plus 25, which is equal to 6,914. We get 691 on one side and 4 on the other. So we take the 4, multiply it by 5, and add that to 691. 691 plus 20 equals 711, which is 700 plus 11. So let's continue to see that this is not divisible by 7 for sure. 71, and the last digit is 1. So we multiply the 1 by 5. We get 71 plus 5 is 76, which we recognize is 1 less than 77. 77 is divisible by 7, so something that's 1 less than would have a remainder of 6, not divisible by 7. So 68,895 is not divisible by 7. All right, so to understand why this works, we have to think about how numbers look. So we have the 4-digit number A, B, C, D. This is not A times B times C times D. What this really is the A is in the thousands place, the B is in the hundreds place, C is in the tens place, and D is in the ones place. So it's really 1000A plus 100B plus 10C plus D. And when we replace this by ABC plus 5D, that's not A times B times C plus 5D. What that is 100A plus 10B plus C plus 5D. Right, we shifted down. The A is now the third digit from the right, the B is the second, and the C is the first, and then we added 5D to that. But we have to unpack this a bit to understand what we're really doing here. So what we're actually doing is two steps. We have 1000A plus 100B plus 10C plus 50D, and then we divide that by 10. Right, and note that this is equal to what I had just written above. When I divide by 10, I divide each of the coefficients by 10. 1000 becomes 100, 100 becomes 10, 10 becomes 1, 50 becomes 5. So what I just wrote down is equivalent to ABC plus 5D, but seeing it this way allows us to understand why what we did works. Compared to the original number, 1000A plus 100B plus 10C plus 1D, we've done two things. In the first step, we replaced D by 50D. We had one copy of D, that plus D at the end, and now we have a plus 50D. So in net, we got rid of 1, we added 50. We added overall 49 Ds. Right, we went from 1 up to 50, so we went up by 49 Ds. And the other reason that we chose to do this is now it makes the number a multiple of 10. This allows us to do the second step, which is divide by 10. And the reason we do this to get this ABC plus 5D that we saw in the steps earlier is just we get a smaller number. Once we have a smaller number, we're either done because we recognize that we're divisible by 7, we're not, or we can do it again and we get closer. So I've broken down these two steps. Let's see why each one does not change whether the original number was or was not divisible by 7. So for the first step, we're adding 49D. So if the original number was divisible by 7, that means we could write it as 7 times k. And this turns into 7k plus 49D, which we can then factor out as 7 times k plus 7d. And we notice k is a whole number, d is a whole number, 7 is a whole number. So k plus 7d is still a whole number, which means that when we add 49d, we haven't suddenly made this number not divisible by 7. If we started with a number that was not divisible by 7, like if it had a remainder of 4, this would turn into 7k plus 49d plus 4. So when we tried to factor out a 7, we still have this plus 4 at the end as the remainder, and this new number is not suddenly divisible by 7. To understand why dividing by 10 doesn't change by 7, let's think about prime factorization. If we have a number n which is written in its prime factors as 2 to the power of a sub 2 times 3 to the power of a sub 3 times 5 to the power of a sub 5 times 7 to the power of a sub 7 times, it has a lot of prime factors maybe, the highest one we'll just call p to the power of a sub p. If we write out n in this way, and we divide it by 10, if we look at the prime factors, 10 is 2 times 5, so when we divide n by 10, all that we're doing is we're getting rid of one copy of 2. We haven't changed how many 3's we have. we're getting rid of 1 copy of 5. We haven't changed how many copies of 7 we have. And the rest of these prime numbers, we still have the same number of each one. All we've done is we got rid of 1 copy of 2 and 1 copy of 5, because we're divided by 2 times 5. In particular, this 7 here still has the same number of factors in the factorization of n. If it was divisible by 7, it still is. We still have at least 1 copy of 7. If it wasn't divisible by 7, we didn't add any copies of 7, so we're still not divisible by 7. So that means that if we take our original number a, b, c, d, and we change it into a, b, c plus 5d, we have this is divisible by 7 if and only if a, b, c plus 5d is divisible by 7. So that explains why this trick works. If you want an exercise, there's a similar trick where you replace a, b, c, d by a, b, c minus 2d. So instead of a plus 5d, we have a minus 2d. The exercise is to show this also works. The process of showing that will be quite similar to the first one, but it's good practice to try a similar problem to one you've just seen to get practice with that.